spacing out. Sorry, people. So I'm very happy to welcome Nahum Arav just for the day to Toronto. Nahum and I have been talking about the sorts of problems he's going to discuss today for basically 20 years. Mm-hmm. And I have to say he's been making really good progress on nailing down where these features are that he's going to describe, how far they are from the central engine and so forth. And I think he's got a great story to tell. So go ahead.
Thank you very much, Norm. Well, it's a pleasure being here. I think it's my third visit to CITA. I'm always honored. I just cannot spend more time I wish to, but when you have 3 small children, you have other constraints on your life. So I'll have to leave after here about 4 o'clock or so. Just leave. Not 4, 5, sorry. 5 o'clock. I won't leave before the end of the talk. So as Norm said, we talk to each other and we know of each other work for many years. One of the many fields that Norm is working on is outflows in AGNs, and he contributed some of the important theoretical papers to describe these winds. So I want to tell you a little bit about the progress that we have made over the past few years in these outflows. So first, of course, I want to mention all of my collaborators, without which I wouldn't be able to do any of that. And I actually want to specifically say some of the work I'll show here today is from my undergraduate student, Max Moe, who, as the old joke goes, was the best postdoc I ever had. So this is always a treat, and he is a first author in a very well-cited paper. So let me jump first to the conclusion. So those of you who want to fall asleep can easily do that. And many of you have seen objects like that. These are broad absorption line quasars. They were discovered only a few years after Martin Schmidt had actually discovered quasars. You see the normal emission lines that all quasars have, and you have these big, broad features which we attribute to outflows. It's the same ions that give you the emission line, but it's blue shifted, so it's material that goes towards you from the AGN at speeds of up to 30,000 kilometers a second. So we know them for more than 40 years now. And for decades, they were an enigma. What are these outflows? Do they have any effect on the black hole? Do they have any effect on the host galaxy? So I want to jump to the conclusion and tell you that from the work we have done in the last 5 years, we claim that the average luminous quasar have subrelativistic outflows like these that are on large scale, of about 1,000 parsecs, so they are galactic in scale. They have very large mass flow rates of 100 to a few hundred solar masses per year, and kinetic luminosity that is sufficient for producing the AGN feedback that a lot of people are working on in the last 10, 15 years. But let's start from the beginning. So the way I like to tell the story is the following. I need to give you a little bit of introduction to AGN feedback. So here is one of the deepest images ever taken of the universe. And I think this is the Hubble Ultra Deep Field. And I think that the beautiful intellectual achievement we have done in the last 20 years is in cosmology goes very much underrated. Because people were able to do with the beautiful cosmological simulations to start from the initial conditions, from the CMB, and the known laws of physics, the metric of the universe and gravity, and produce in the computer universes that are very similar to this. I think this is remarkable. You know, we create the full universe in the computer. I don't think we celebrate that enough. I have nothing to do with that, by the way. So here is the universe circa 1400. This is the cosmology of the Middle Ages. You see the sphere, and you see the clockwork machinery that moves everything in the background. And here is the monk that got all the way to the end and speaking. And let me show you the modern version of that, thanks to my friend Andrei Kratsov in Chicago. And I'll say OK. And you've probably seen a lot of these things. So God created the universe in the box. It's much easier. And you have the time goes by, redshift goes lower, and time goes all the way to here. And you've seen these things. This is just a beautiful current simulations, 100 megaparsec on scale, giving you the filamentary structure of the universe. And I think many people in the audience know about this stuff much more than I do. So this is all wonderful. And yet, there are a few problems in the real universe that the real universe is not matched by the simulations. And for these problems, a lot of theoreticians are claiming that mechanical energy injected from the AGN, from the supermassive black hole, will solve these issues. So I'm going to very briefly talk about a few of these and give you a plethora of theoretical papers that are using that kind of energy input from the AGN in order to solve that. The first is cluster cooling flows. The idea is that a lot of gas in the cluster is supposed to start cooling and flow toward the center massive galaxy. And that was predicted with big brouhaha, and we don't really see it in X-ray. What we see is a highly disturbed environment with high entropy. Something has to energize that or put an entropy in this material, and AGN to the rescue. The second thing is the evolution of the host galaxy. The simulation tends to give us too many massive, large galaxies. The universe does not supply that, and the idea is that a huge wind from the center black hole will develop and will push out the gas reservoir of the galaxy out, curtail the growth of the host galaxy. The growth of supermassive black holes, we know the famous M-sigma relationship. Why should the tiny little black hole in the center will know anything about what's happening 8 orders of magnitude larger in radius around? Why is the tight correlation between the mass of the bulge and the mass of the black hole? AGN feedback, the feedback between the kinetic energy coming out of the black hole and the halo will do that, or the bulge. One last thing is the enrichment of the intergalactic medium. Galaxies are very good in producing metals, but they're also keeping them in a strong gravitational potential. If you want to, not nicely to say pollute, or nicely to say enrich the intergalactic medium with metals, you want something to take the metals from the galaxy and move them all around, because we know that the IgM had some metallicity and it's not pristine material from the Big Bang. So the idea is the following. The mass of the black hole is very small compared to the mass of the galaxy, about 1,000th. But the potential energy of the black hole is huge. And let me just give you the physical argument why. The potential energy of the galaxy per unit of rest mass is simply, can be estimated as the rotational speed divided by the speed of light square. It will basically, I'm evoking the virial theorem, but because the velocity around the galaxy is close to 300 kilometers per second, you get 10 to the minus 6 in these units. So potential energy per rest mass energy. But a black hole is a relativistic object. So a significant percent of its mass in the form of potential energy. So if you can tap even a little bit of that, if you can tap a few percent of the energy that was constructing the black hole into a mechanical outflow that will interact with the galaxy, you have enough energy to disperse the whole galaxy. It's a simple energetic argument. This is why theorists love this, because there is a mechanism that can give enough energy to do all of these things they talk about. And why is it feedback? Because if the black hole grows too much, it blows up all the material around it and starve its own growth. So there will be something that will regulate the growth. OK, so I told you about my favorite object in the universe, the AGN outflows. And here is an object that we observed with 40 orbits of HST a while ago. And the question is, how do you go from looking at these absorption trough that we say are winds, how do you get the size and the physics of what's happening there? So as everything in physics, what we're going to do is we're going to build a very simple model. So let's start with a simple model. What we really want to know for quasar contribution to AGN feedback is we want to know the mass flux and kinetic luminosity. That's what the parameter that will drive the physics of the situation. So let's assume the spherical cow model. We have a AGN here. We have an outflow that is going out as a thin shell at velocity v. And then we need to know 3 things. Velocity is actually very easy because you get it from the Doppler shift in the spectrum. That comes almost for free. But what we want to know is the mass per unit area. which in astronomy we call column density, of course. That's the first thing we want to know. The second thing we want to know is the size of that sphere, because we need to have, it will be 4 pi r squared for the entire sheet. So we want to know the distance. And it is obviously not going to be a spherical wind, so there will be some solid angle omega that we will need to say something about before we'll be able to translate these numbers to actual values. And how will it go? Well, it's quite simple. If you think about it, the model I showed you, the total mass of the sphere will be 4 pi omega times r squared nh times this coefficient, which is the mean molecular weight of the plasma times the mass of the proton. That will give you basically the mass per unit area, and this is the area here. And then we use the simplest approximation for the mass flux and kinetic luminosity. We'll simply divide the mass by the dynamical timescale, divided by r over v. So we get this expression, and for the kinetic luminosity, we take half m dot v squared. So the kinetic luminosity at the end of the day with our observable will be dependent on the omega 1 power of r and 1 power of nh. So our mission, our task is to get these numbers and to know something about this number, and we are basically done because it's a very simple algebraic equation here. So here's the situation up until about 2008. In the same objects, people had claimed that the column density differ by 4 orders of magnitude. Now, even in astronomical terms, this is too inaccurate. The radius is a little bit different. There were good arguments that some objects, the winds were very close in, 0.01 parsec, but there were also outflows that were found at 10 kiloparsecs. So it's obviously that you need to find many single objects where you can have both the distance and the column density.
And did the product n times r vary over that vast range as well?
Well, yeah, of course. And this is why it was kind of nonsensical. And omega, interestingly enough, is the easiest thing to estimate, or the one that has the smallest variations. And that comes from a very simple observational explanation. 20% of all quasars show these winds. So you can either say that every single quasar has a wind that covers 20% of the area, or else you have 20% of the quasars that are covered by 100% wind. But for the global energetics, it basically cancel out. It's the same thing. And it's also the same if you say that it's time variable. So all of these are basically the same thing. So we can work with omega equal 0.2 and be happy with that.
Well, obviously, it doesn't have a big impact on the physics of feedback.
Yes, of a single galaxy, it will, definitely. But again, the factor will be only a factor of a few, where here you have 4 orders of magnitude, and here you have 6 orders of magnitude. So I better concentrate my efforts where the unknowns are bigger.
Yeah, but if you want to explain the end simulation in a conventional way, for example,
Mm-hmm.
one look at it better be directed right at the source of the gas that's
True.
feeding the
True.
whole.
One of the nicest thing about these winds is because they are wide, they will interact with much more material in the galactic environment, for example, compared to relativistic jets. Relativistic jets are pencil beams, and it's very difficult to couple them to matter. But good point. OK. So how do we go from the spectrum to measuring kinetic luminosity? I don't know how many of you guys have seen spectra of these objects. This looks like the run-of-the-mill bulk QSO. It's actually not too similar to Norm's favorite object, PHL 5200. This is the world record for kinetic luminosity in the universe. Okay? How do we know that? What do we do? Okay? So here is a brief version of the story. This is the SDSS data of this object, by the way. So what we do is, we first of all need to get the physics or the amount of column density in the ion we observe. So remember, we have a trough here. This is carbon 4. We need to convert this absorption trough into column density. Now, this is done in astrophysics for more than 80 years, in stars, in ISM, in AGN. And most people just say, well, give me the equivalent width. I do the curve of growth. I'll know what's happening. I will show you one example how much trickier this stuff is. You can get wrong answer by a factor of 1,000 if you do it for the outflows. So here's the example I want to show. This is a trough of an outflow showing in velocity presentation, and I show 3 troughs on top of each other. The black is carbon-4, the blue is silicon-4, and the green is phosphorus-5. Okay? Now, you can see something interesting. The carbon-4 is not black. It definitely has residual intensity here, which with this extremely high signal-to-noise is very obvious. So if you do the nominal calculation, the apparent optical depth of carbon-4 is 3. What do I mean by apparent optical depth? Is when you do the simplest thing like you do with the ISM and IGM, you say that the residual intensity equal to e to the minus tau, when we call it the apparent optical depth. If you get the optical depth and you integrate the optical depth over the trough, over the velocity, you're basically done. You get the column density. Okay? But normally, in, again, ISM and IGM, you just need to work with the apparent optical depth. Here, I'm going to show you that the situation is vastly different. So the optical depth in carbon-4 here looks to be 3, while the optical depth in phosphorus-5 looks to be 2. Now that looks very innocent, but actually it's very not innocent. Why? Because phosphorus-5 and carbon-4, in ionization, they track each other as a function of ionization parameter. So the ratio is about constant, so you would expect them to be in the same ratio everywhere, but phosphorus is 1,000th as abundant as carbon. Because their oscillator strength and wavelengths are very similar, you would expect that if the carbon-4 optical depth is 3, phosphorus-5 optical depth will be 3 divided by 1,000, because it's 1,000 times less abundant. And all the other parameters are basically equal. But this is obviously not the case. You have an extremely deep trough here. So in the early 90s, the fashion was to claim that these outflows has phosphorus abundance that is 1,000 times solar. There were people who wrote papers like that. When I saw that, I decided that something is very wrong here. And basically what we have is that this trough is extremely saturated compared to phosphorus-5. Phosphorus-5 might be optical depth of 2, but that means that carbon-4 needs to be about optical depth of 2,000.
So some you're saying it's on the other side of the curve of birth?
What?
You're saying it's on the other side of the curve of birth?
No, what I say is that there are other effects. The stuff that is bringing the light here is because the outflow does not fully cover the source. The source has a big area, and the outflow only covers, let's say, 95% of it. So it doesn't matter how much material you have in front of that, the maximum depth you'll get is 95%. You will never get below that because it will be freely streaming photons. So in the late 90s, people accepted this explanation, but we never had the smoking gun. And here I'm going to show you the smoking gun right now. In this outflow, we were able to show that the column density of sulfur-4 equal 60 times the column density of phosphorus-5. Okay? Why is this important? Because both these are also tracking each other in ionization quite well. And basically what that says is the ratio of 60 between sulfur-4 and phosphorus-5 equal exactly to the protosolar ratio of the elements. If you look at Asplan and Grives, for example, sulfur in the universe is 60 times more abundant than phosphorus. So what we say is very simple. This outflow has protosolar metallicity. We just found that because we found the actual column density of sulfur-4 and phosphorus-5. So if it's protosolar metallicity, we can then go and assume that carbon is also protosolar metallicity. But carbon over phosphorus is 3.
Now you just showed that you can't trust anything you do here. So how do we know that we can trust your?
Excellent. I'll show you in a second. In a second, I will give a hint. I didn't want to put too many transparency for that, but I will show a hint in a second. So here, I'm going to say that the abundances of carbon over phosphorus is a factor of 1,000. And therefore, we said that the column density of carbon-4 should be 1,000 times the column density of phosphorus-5. You translate that to optical depth, you see that the actual optical depth in carbon-4, the real optical depth, should be 1,500 times the real optical depth of phosphorus-5. I will argue that this is a real optical depth. I'll show you in a second why. So the optical depth in carbon-4 of this innocent trough is 3,000. Okay? So we have the smoking gun. We actually show that indeed you hide 1,000 times more column density in this unassuming carbon-4 trough because it is extremely saturated, and the little amount of light that comes through is because of geometrical effect covering factor. So I'll show here an example in a second. How do we do that with sulfur 4? So the next thing is to measure the physical conditions, basically the ionization parameter and the full column density. And what we do is the following. We take a quasar spectral energy distribution. We take that SED and we put it in the oracle of Cloudy, the Cloudy photoionization code that does all the calculation for us. And we basically say the following. We move it through a sheet of material. We specify the column density of the cloud. We specify the ionization parameter of this SED. And we then ask to find the column density that we derive. And here for Martin's question, this is the money plot here. This is sulfur 4, and this is sulfur 4 excited. Now you can see something interesting. We expect sulfur 4 to have twice the amount of column density as sulfur 4 excited, but we modeled both trough with the exact same Gaussian. So they are obviously saturated. But look at this little thing here. There is a side trough here, which is the second excited level of sulfur 4. That level has an oscillator strength that is 1/10. So you're going to expect that if this was not very saturated, this will be 1/10 as deep, so it will be somewhere here. But because this is much deeper and yet not as deep, I can get the exact column density. So these are the kind of techniques we use. And phosphorus 5, we do the same thing because it's a doublet with ratio of 1:2. So we take the column density measure here and ask Cloudy to give us the combination of ionization parameter and column density of hydrogen that will reproduce that. So how does it work? Here is a grid model of Cloudy. What you have here is thousands Cloudy models. We take a grid of models from 10 to the 16 to 10 to the 19 in column density, an ionization parameter, which I'll define in a second, from log of -2 to 1. And then I say, OK, I measured a specific amount of hydrogen, in this case, log of 20.86. What is the locus of points on this plane that will give me this result? So you can get this amount of neutral hydrogen if the cloud is relatively neutral. It can be very thin, only 10 to the 16. Or if it's highly ionized, you will need much more hydrogen because the percentage of neutral hydrogen is much less. So it will follow this line. OK, so we did.
Those ionization parameters, don't you have instabilities in the, like you couldn't have a uniform?
No, these are actually very mundane ionization parameters. It's only much higher that you start having problems. So what you're going to have is all of this is going to be on the locus of these points. OK, so we reduce the problem from a full plane to a line. We want to know the axial solution. It will come if you give me another measurement. Here is a measurement of oxygen 6. And oxygen 6 behave differently because there are many different ionization species. This is where oxygen 6 peaks. That is the ionization parameter that it has the maximum fraction of ionization. Here you're dominated by oxygen 7 and 8. Here you're dominated by oxygen 4, 3, 2, and 1. And nicely enough, the only thing I need to see is the crossing of the two curves, and I get the physical solution. I can read from this the total column density of the cloud, this thing, and the ionization parameter. And voila, I have two very important numbers that I need. Remember that one of them, NH, is already going to be in our equations for the mass flux and the kinetic luminosity. OK. Next.
Sorry, do you have a third line system that you can do to get a check on this?
Yes, many times. And I'll show you in a second. Normally, we have like 7, 8, 10.
And do they agree, or do they disagree?
They never cross exactly the same point, but within the error bars, they agree very well. And I'll show you how, when they disagree, you can start showing that a model of a single ionization parameter doesn't work, and you have to go to 2 or 3 or more. And this will be very important later. It's very good.
Just to be skeptic here, those two curves are almost degenerate. I mean, what are the error bars in these?
Yes, it's very important to have the error bars. And when I actually show you the real case, I'll put the error bars in them. Yes, this is just for show. Yes. OK. So then, by the way, this is Genzel shooting the center of the galaxy from the VLT. We get most of our data from VLT, where we are very thankful for the VLT TAC for giving us a large amount of observations to do all of this work. Okay, so now the Holy Grail, we need to determine the distance from the outflow, from the central source to the outflow. So here is my explanation of kind of a little bit of dichotomy in the field. There are a lot of people who worked in the field 20 years ago until rather recently that have a picture in their mind that the outflow should be very, very close to the black hole, the outflow that you see. Now, why? Because other astrophysical outflows are very close to the source. Here, you can see P Cygni profiles. And P Cygni profiles basically start from the photosphere of the star. So right at the radius of the star, the wind starts, and you get this nice P Cygni absorption profile. And here we can see theoretically why it should happen and things like that. And so the expectation was they start from basically wherever you have material. In CVs, we have known disk winds. They start from the accretion disk around the CV. So why not, having these distances for AGN outflows, also be right at the accretion disk? And indeed, many models have that. And this is a famous cartoon picture by Martin Elvis that has the winds coming from an accretion disk. This model doesn't have any dynamics. It just shows the phenomenology. But you can see that the expectation was that the wind is launch and accelerate at around 10 to the 16 centimeters, so a little bit less than 0.01 parsec. Okay? But where the winds are is not a theoretical question. It's an empirical question. We actually need to observe it and see and try to figure out the distance. So how are we going to do it observationally? We're going to do it this way. This is the ionization parameter. The ionization parameter physically is a very interesting ratio. It's the ratio of number density of ionizing photons divided by the number density of hydrogen of all species. And obviously, if the number is higher, the plasma will get more highly ionized because you have more photons to do the ionization. And indeed, the fraction of neutral hydrogen is inversely proportional to the ionization parameter. So the actual definition will be the number of ionizing photons radiated per second divided by 4 pi r squared in speed of light c and NE here. So you can see that there is an interesting degeneracy. For the same ionization parameter that we solved just a minute ago, okay, we know the ionization parameter of the outflow. It can be either very far away if n is very small, or very close by if n is very large. So we need something to decouple or remove this degeneracy. If we do very sophisticated algebra, we can solve for r. And what we need to know for r, remember this comes very easily. This is the number of ionizing photons. We just need to know the flux and the redshift of the object. The u we already solved for, and the rest are just parameter except the number density. How do we go about the number density? We use atomic physics. Lines, spectroscopic lines, come from different levels, and sometimes we can have a population of electrons in an excited state or a metastable state. The ratio of the amount of electrons in the excited state to the ground state is very sensitive to number density. Why? Because the more collisions you have, the higher the population of the excited state is. So these curves show you several different ions that have excited states and resonance state that by the ratio of the excited to the ground or the resonance level, you can map the electron number density. And you can see that we have lots of these guys here. Now, here is the actual determination from one of the objects we have. Now, because we already know the u for that object, we can translate the number density to distances, and you can just read the distance from here. So it becomes rather simple, and my battery just died. You get it right here. Do you have another pointer, someone?
Stick there.
Stick is very good. Okay. So we have a distance here already, I'll give up the secret, of 3,000 parsecs away from the source in that specific object. So now I'll have to just be here. So let me sit down. good time for the battery to die. Okay, so how do we do it in real? So here is an SDS spectrum that only its mother can love. Okay, this is noisy. This is, looks totally like crap, except that this took an undergraduate student of mine about 2 months in the summer to find. And because of that, she's on the paper of what we did with that. Because what I do is I send my undergrad students to hunt in this SDSS Quasar survey. And there are 50,000 good Quasar spectra there. So they go through that and search on a very specific parameter search that I tell them to do. And they produce these plots where they identify where all of the different lines are. And I want to show you specifically 2 lines. Here is sulfur 4, and here is sulfur 4 excited. The ratio of the column density from sulfur 4 excited to sulfur 4 will give me the number density of the outflow and therefore its distance. Now, I can't do anything with this crap data. This is just good for identification. Then I go and I send a proposal to the VLT asking for decent data of that object. And a year later, if I'm lucky, I get the data and I look at what's happening and see if there is Christmas in July. So, by the way, our good friend Kramer had first published these lines in NDC 4151. And one of the nice things about what we do in astrophysics, we learn from all of the people working around us. So I seized that and I said, I'll go and search that in real quasars and see what I can do. OK, so you know the story now. So we look at the phosphorus 5 of this object, and we model it with a rigid model that will apply to all other ions, and we get the column density of phosphorus 5 from this. With that, we get your. This is all IGM. This is a redshift 2.8 quasar. And the nice thing is with that kind of resolution, I can ignore them because the trough is much wider. It took us a few good years before we had the courage to work in the forbidden forest, the Lyman alpha forest. But now we do it with a relish because we know we develop all the techniques and stuff, so we can work on that. So for your question, this is really how it works. These color bands are the 1 sigma error bars over that. And what you can see is all of these things are degenerate, and it's phosphorus 5 that breaks the degeneracy. So the solution for the outflow has to be here, and it is and this parameter of about minus 0.5 log, and column density a little bit more than 10 to the 22. These lines are just upper limits, so they allow everything below this, so they're consistent with the solution. OK, so we have the column density in the parameter.
So it really is all your power is coming from the phosphorus.
Yes, the diagnostic power here from phosphorus. Sometimes I do it with helium-1 excited, because again, helium-1 excited is a very rare ion. It's 10 to the minus 6 of helium-2. So that works very well.
Of course, would like to have, I guess, at least 2 or 3 line ratios optimal.
Yes, yes.
That were really constrained.
Yes, and sometimes we're lucky and we have that. For example, we have a secret object that I'm under embargo. I can't tell you guys that I showed Norm today, though, and has 2 of these ratios that are exactly the same. And we have published an object in 2008 where 5 iron lines pairs give you the exact same ratio also. So yeah, whenever we can, we try to do that to control systematics as much as possible. Yeah.
So the solution to the line transfer problem is having very clumpy material.
Yes.
But some of your material seems to be covering the entire source. So you probably have a distribution function for density within at any one place, not just along line of sight. So do these all have to line up if you have a distribution of different densities?
Well, we put a lot of thought into that, and basically what we did was we started with the simplest idea that everything is fully covered by the exact same optical depth. This is the apparent optical depth method, and we showed that it's disastrous because of all the things I showed. Then we worked with models that are partial covering, saying if this is the source of light, maybe it just covered like a brick, half of it or 80% and stuff. The next approximation we did was a little bit in your vein when we said, let's use a distribution of column density across the source. And that is actually the solution that fit the data best. When we go to 3-parameter solution, we don't get any improvement in our results. So while the situation is probably very complicated, empirically and mathematically, I don't need to go to more sophisticated models in order to describe my data. Maybe if I'll get 1,000 signal-to-noise data and I'll have a series of 10 lines, I'll need to, but for what I have right now, a model with 2 parameters and a distribution more or less like you said of a different column density in front of each point of the emission source works.
Blobs,
yes.
Characteristic density.
Yes.
And then they go optically thick and so on.
Yes, yes. And also you can think about it, a clump, it can be very thick in carbon 4, but very optically thin in phosphorus 5. So that will explain why you get different saturation in different lines. So yeah, we only work 5 years on that. So, and I'm telling you the very short version of it. So here is a sulfur 4 and sulfur 4 excited. So with the ratio of this to this, as you know, is going to give you the number density. And here is the number density. We get it here. It is about 4.3 in the log, the NE. And once we know the ionization parameter from here, we can get the distance. In this case, the distance is 300 parsecs. So now I know everything. I know the distance. I know the hydrogen column density. I assume omega of 0.2, because this is just the run-of-the-mill bulk here. So the algebra is trivial, and it gives me this. Okay? This is a short entry of a table. This is a telephone number of that object. We have reason to believe that it has supermetallicity, so we use 4 times solar, which actually minimize the amount of mass that is flowing. So it's a conservative estimate. The speed that it moves is at 8,000 kilometers a second. It's a monster quasar. It's one of the brightest objects in the universe, 10 to the 47.2 ergs per second. And now look at the number that we have. Okay. As I said, the distance is about 300 parsecs in this case. The kinetic luminosity of this outflow is 10 to the 46 ergs per second. To give you an example, the entire bolometric luminosity of the Milky Way galaxy is 10 to the 44. So that monster has 100 times more kinetic luminosity than the entire Milky Way galaxy is radiating. The next thing is, this is a very important number. The percentage of, I say here L ball, but because it's a very high, it is a very bright quasar, its redshift, it's very close to the Eddington limit. And the important thing is that we produce few percent of the Eddington limit, and in the work by Scanapioco and by Phil Hopkins, if you are in the ballpark between 0.5% to 5%, you're going to produce very strong AGN feedback. So we have that. And then last but not least, look at the mass flux rate. It's almost 400 solar masses per year, which rivals the star formation rate for the most star-forming objects in the universe. So without any other calculation, what you see in front of your eyes is a wind that's vacating the entire reservoir of star-forming gas because it's competing with the actual star formation rate. Okay. Yeah.
Cool question. This gas that's doing these orbits is around 10,000 degrees.
Yeah, but something like that. Yeah.
So the ratio of thermal, I mean, it's moving at one heck of a Mach.
Yes, yes. Very fast. Another thing that Noam likes to look at is the issue of the momentum limit. If you take the single scattering limit, like many people use in O-star winds, they say that a photon gives all of its momentum to the wind, then there is a limit that you say that m dot v divided by L over c cannot be larger than 1. This outflow breaks it by a factor of 20. So you either have to extract the energy from the photon, not just the momentum, like by scattering it many times, or else find another ways of accelerating the wind. Okay, and what was that? Never mind. So let me just show you that we can do even better once we work with space-based, with basically HST. Why? Because one thing that I forgot to mention is that all of the lines we probe, this carbon 4, phosphorus 5, are relatively low ionization species. And our friends in the X-rays, when they look at winds from Seyfert galaxy, where they can see the X-ray flux, they see lines from oxygen 7, oxygen 8, all the way to iron 26. That column density tend to dominate. It tend to be between 3 to 50 times more than in the colder phase that I just showed you. So obviously, if I'm not going to account for it, I'm always going to miss a big bulk of the material that is moving. So the nice thing is the following. When we started working on that, both from the ground and with HST on low redshift objects, the lines that we see are basically Lyman alpha nitrogen 5 carbon 4 in these wavelengths, and few cases of silicon 4, but basically everything that is above 1,000 angstroms. There are not too many lines. We don't have many diagnostics. However, if we can access the rest wavelength from 1,000 to 500 angstrom, look what happens. We have a plethora of diagnostics here. And I give you 3 kinds of diagnostics. The black are the resonance lines. The red are excited states. So you can see that in this case, we have 12, 15 pairs that we can use instead of the 1 or 2 that we can use longer wavelength. So if we can observe that range, it will be fantastic because our measurement will be so much better. The next thing, and not less important, is the fact that we now can observe oxygen 6, neon 8, sodium 9, magnesium 10, and even silicon 12. They are much higher ionization. They start probing the very hot phase of the outflow. So I can start seeing with that what our X-ray friends need 1,000,000 seconds in Chandra, I can do with 10 or 20,000 seconds with HST. It's a big time saving. And it's an object that actually matters in the universe. It's the big luminous quasar that's doing feedback, not the measly little Seyferts that we have. So what can we do? If we can observe objects that are redshift above 0.2, basically, all the way to 1.2 or 1.5, we can observe the rest frame from 500 to 1,000. Now, we couldn't do it until recently because the instrumental space telescope were not sensitive enough. But 4 years ago, we got beautiful COS spectrograph that increases sensitivity by a factor of 20. And now we can do that. So let me show you the first example we had published. So by now, you are experts on all this. So I can just show you the brief of it. You don't see double. These are 2 outflows, A and B. You see them in the red neon 8 doublet, and this is in the blue. This is about 4,000 kilometers a second. This is about 5,000 kilometers a second. So they are very respectable speeds. Because it's neon 8, I have a probe of the high ionization material. This little guy is not less important. This is oxygen 4 excited, and this is oxygen 4. The ratio of these 2 guys will give me the number density. So you already know that if I have a combination of these guys, I will know both the column density and the distance of the outflow. And indeed, the ratio that I get here, in this case, it was a little bit less than 10 to the 4. And here is what I said before. This is now what I get for measuring all of these lines. Here is neon 8, here's magnesium 10, oxygen 4, oxygen 6. If I try to model that with one ionization parameter, I get a committee solution. This is a terrible solution because it misses the oxygen 4 by 6 sigma and misses the oxygen 6 by 4 sigma, and it's just a chi-square solution that obviously is unphysical. So this outflow cannot be described with one ionization parameter. Now, that did not come as a big surprise for us because our X-ray fellows for the last 12 years are telling us that when they see all these ionization stages, they have to model them with 2, 3, or even 4 ionization parameters. So this is not it didn't come as a shock. So in another term, the difference between the ratio of the observed to the ratio of the model is 50 times. And this is just unacceptable. So what do? We go and say, OK, let us try 2 ionization solution. And in this case, 2 ionization solutions give us a perfect match. Why? Because you already saw that there is a whole bunch of lines that beg to have an ionization parameter here. So if you have one here, and then I show you a little bit larger, and then another one that will actually take care of some of the hydrogen, but mainly oxygen 4, and I don't show you here about nitrogen 4 as well, then I get a perfect solution. So the outflow is dominated by a factor of more than 100 by the high ionization phase. And the distance is coming from the oxygen 4 that all reside in the cold phase, which is at 3,000 parsecs away. So I can do the exact same trick as I did before. Oh, and we can also monitor, you might ask, what happened if you use different SEDs? So I have all of these plots here to show. What if you use different metallicities? We can explore the parameter phase. And indeed, here we have like 12 models in each of them to show how that works. But the essence of that, it doesn't really change. You have one phase that wants to be here, and one phase that wants to be here, and it doesn't really change either for the trough if you change the metallicity or you change the SED. So we've done all that.
Now you don't know necessarily that they have the same distance anymore, right? They don't have to be at the same distance anymore.
This one and this one? But they have, and I'll show you why. This is because, well, I don't have the velocity plot, but the resolution is phenomenal. The centroid here is exactly the same as the centroid here. I get it as the exact same place. So you can see this, for example. You see, these two show you the exact same velocity position as these, and you can see that there's a correspondence of 1-to-1 between the position here to the position of the trough here.
It doesn't have free components, though.
It's true. I'll need to show you exactly in velocity, but the correspondence is good, and more than that, it's less than 500 kilometers per second wide, and the question is, why would...
Two shells.
Exactly. In exactly the same velocity, yes.
So your two ionization parameter solution is two densities at the same radius.
Yes, yes, exactly. And the one that is the higher ionization is having much more column density, so it's really occupying much more of the volume. The filling factor in this case we get for the cold phase is about 10 to the minus 5. So we expect the hot phase to fill all the volume, and the cold phase is little blobs that are only filling 10 to the minus 5.
Still trust your electron density for the cold phase. That cannot be the same as for the hot phase.
Of course not. The column density, where is that? The number density comes from oxygen 4.
Yeah.
So what I'm saying is I get the number density just for the cold phase. The number density for the hot phase is just the ionization parameter difference, because that's the only difference that can happen. So it will be a factor of almost 100.
Do you have any indication if the difference in density is due to turbulence or thermal bistability or some
No.
other process?
It's for other people to discover. I don't have empirical evidence for that. But it is a question of knowing on us. There's no question about it. We would like to know the microphysics of what's happening.
Did you know the temperature for each of these phases?
Well, the temperature for this one is easy. Now, here there is an interesting issue, and I wrote on that in the paper. If I assume that it is just photoionization, then I know the temperature here because the photoionization solution give me, and then these two are not in pressure equilibrium. This phase has about 30 times the pressure on this guy. But this is when I assume a pure photoionization model, that the only thing that makes the plasma hot is the photoionization. If I have any kind of other heat source, like shocks, then I can heat this phase quite a bit and still keep the solution in the same place and get them to pressure equilibrium. Now, I don't claim that there are, but I claim that there is at least a theoretical possibility that I will find them in pressure equilibrium. The simple photoionization model cannot have them in pressure equilibrium.
So is there any reason why you have a wind which has a different radial dependency, and what you're seeing, the low ionization is in this shell and high ionization is in that shell?
Well, as Martin said a few minutes ago, we use kinematic correspondence. If we see the oxygen 4 moving at the exact same velocity as a neonate, that should be the same shell.
Well, I understand you're confusing, and you say they're the same shell, but what happened to the ones which are closer to
Well, what you're going to have is this. Why don't,
You have 3 shells there, right? So are the other 2 shells different?
what 3 shells?
Well, we have the 3 components, or is that 3?
Oh, yeah. So we do have a little bit of a difference here. I didn't get into the minutiae of that, but yes, we do have more structure here and here than we get here. But this is because we are going to detect the oxygen 4 only in the one component here that is the thickest of them. So it does correspond to exactly one of them, and we deduce for the other ones. And we have a slightly more delicate analysis in the paper.
It's a time-dependent situation. This wind's been blowing for however long you get there. Why shouldn't we just different layers by looking at different ionization lines?
It's a very good question. And one of the models that show that is the paper that Norm is on by first author is Claude-Henri Refouché-Guillaume. We always assume that the wind is just going in shells like that. What the theoretical model that they have is you have a hot wind that is now bouncing into ISM clouds and things like that and make the wind a local phenomena from the surface of that cloud. Okay, so it actually is very localized, and it's probably time dependent because it might not live beyond, I don't know, 10 to the 4, 10 to the 5 years, but it's not a phenomenon that the carbon-4 troughs are not going to start from the accretion disk and go all the way to the end of the galaxy. I'll show you in a second. Yes?
Top right. So that's the ratio of this excited state of oxygen 5 to the...
Oxygen 4 excited to oxygen 4 resonance in the 2 different troughs, yes.
Okay, just to understand, so as the density is going up, the excited state is becoming more calm.
Yes.
Why is that?
Because there is a equilibrium between the process that is populating the level and the process that depopulating. The process of depopulating is only dependent on the Einstein A coefficient. It's a rate of, it's just a probability. The process of populating it depends linearly on the density because it depends on collision. Yes, exactly.
And there's no solution where you have some collisional de-excitation as well.
It can happen, but Claudy can tell us about that in the plasma, and in this case there is none. If you have extreme radiation environment, it starts happening, but Claudy take all of that into consideration and can tell you if you are under these conditions or not. And of course, here it's saturated when we become Boltzmannian. Okay, so the very cartoonish picture that we have then is that we have a wind at about 3,000 parsecs from the central source of the galaxy, moving at 5,000 kilometers a second, and can do lots of things. So here is the microphysics of that. As I said before, this is the filling factor of about 10 to the minus 5. So the number density of the cold globules is about 10 to the 4 per cubic centimeter, with a filling factor of 10 to the minus 5 of this much hotter plasma. And the full column density of mainly the hot phase is 10 to the 20. So what will be the consequence for AGN feedback if you have this kind of a big hammer? Well, if you be generous and say that the duty cycle of a quasar is 10 to the 8 years, I take about the maximum that can happen, then such kinetic luminosity of 10 to the 46 ergs per second will give you 10 to the 62 ergs over the lifetime of the quasar. This is enough to inflate McNamara very famous bubbles in the biggest object that he sees. Okay? Now, I did not say that it does it. I said that we have enough energy. If the process actually happened is a very different story. But we have enough energy. And again, due to the larger opening angle and higher mass flux, these absorption outflow may be more efficient for AGN feedback process than AGN jets because, as the old saying, if you want to hit this room, you're not going to use a laser beam. You want something that will affect a large solid angle.
Something nicely aligned with radio lobes. I thought those were actually fairly obviously jets.
There's definitely is. Now, here is a question is whether you're going to have the outflow that we see as a bicones around the relativistic jet. So they will produce exactly the same thing. They will be symmetric around that. So you can easily invoke that, although we just don't know. We don't know the geometry of the alpha because we only see the line of sight. We don't have the nice pictures.
Sometimes you have radio jets, don't you?
Yeah. No, the idea is that they're aligned along the same axis, and you actually will have a radio jet. Yes. Question there? Okay. So we just show here a very colorful plot of how you can get chemical enrichment. We know that in the intracluster medium, a number that we find many times is that the intracluster medium is about 1/3 solar metallicity. If you take these kind of outflows in the supermetallicity, we find them, what the lines here tells you is which kind of galaxy halo you can populate to that metallicity with a given outflow. So with the outflows that we have, we can get up to 10 to the 12 solar masses halo populated with the metallicity that we see. So again, using the mass flux this time, not the energy. Okay. As we said, for dynamical models, we see many of these cases where the outflows is 10 to the 2 to 10 to the 4 parsecs, very, very far away from the AGN. So we need to start thinking about models. How do we create the outflow that we see in these distances? Because they might start from the accretion disk, but the observed phenomena is happening much further away. So a physical explanation of that would be good. And again, I quote Claude André's paper for that. And then we have filling factor, as we said. We have 10 to the minus 5. This is an old issue we have in bulk QSOs coming back again. And for the gas flowing galaxy, we basically, the hypothesis is then that most galaxies experience this violent period of high energy, high speed outflows during their active quasar phase that influence at least their inner 1 to 10 kiloparsecs. And these episodes might have been the most important events in the relationship between the supermassive black hole, the host galaxy, and other structure around it. So summary, I'll just put all of this. And I want to show you our 3 best example. This is a science that is done in object by object because the analysis is very complicated. We would love to do a sample of 500, but it's difficult. So we increase them very slowly. These are the 3 strongest candidates from the 3 strongest outflow from the 10 or 12 that we published. And this is the one that has the 2-phase outflow. This is what we said, the world record holder at 10 to the 46. And this is the one that my undergraduate student, Max Moe, had published 4 years ago. And what else can I say? You can read for yourself. Thank you very much.
Do you see the closer in outflows at any wavelengths when you say they must be much higher? Is that what
we think, well, the warm absorber is a tricky issue. There are claims in literature that X-ray people think that they see them very close in. But the X-ray data is always very starved for photons. So the interpretation are very difficult. On the other hand, we have, in the best example of warm absorbers, the kinematic correspondence of the warm absorber to the UV phenomena is very good. So it seems like they are exactly the same outflow. So if you find the distance of one, you should know the distance of the other. We, with our UV distance indicators, we have cases where if the outflow wanted to have a very high number density, the density indicator will tell us that. We've never seen an outflow with like 10 to the 10 number density that will put it at the edge of the accretion disk. So, but all of this is still very small number statistics. My feeling is that the outflows are stretching all the way from rather close to the accretion disk. I don't know how close, but maybe 0.1 parsecs or even less, all the way to 10,000 parsecs. You see them on all scales. And from the 12 good examples that we have, they seem to be roughly spread logarithmically. So every decade, you have about the same amount of outflows. But for that, I really need about 100 before I can say anything conclusive, because resting this on 12 cases is a little bit thin.
So not knowing all the history of this, I presume one major reason that Elvis was focusing on 10 and 16 centimeters is roughly where the escape speed is.
Yes. Yes.
So getting back to your numbers here, the amazing thing about this is that your outflow is producing a certain kinetic luminosity in core stuff. Mm-hmm. So it has the capacity, obviously, to entrain much more material at a speed about 1/10 of the speed you're measuring from the line limits.
Yes.
Right. But from the Doppler shift.
Mm-hmm.
And it doesn't do that.
I lost your point.
Well,
You say,
This
do
is
you
relatively
see
close.
stuff at absorption relative to systemic of 100 parsecs, I mean
Yeah.
100 kilometers a second or 1,000?
Yes, many times we see. Yes.
so I mean, the issue is that
So
the
if he
stuff
does
is-
see that, he just isn't describing it here.
Okay.
That's the point. You see it at all
Yeah,
ranges, a range of velocities.
Yeah, the range of velocities are very easy empirically to find, and actually there are more outflows at lower velocities than higher velocities.
Yeah.
But with bulkiest,
He's going for the most spectacular
What's the
ones.
relative kinetic luminosity between these different velocity output?
well, for that we need a significantly a higher sample. We do see the kinetic luminosity goes like the third power of the velocity. So everything else equal, it's a huge difference.
Sure. But the radius obviously is not big.
Yes, that is true. But and again, these two things together. So we do have lots of outflows at lower velocities. For example, the CFET outflows that are only a few hundred kilometers a second, they never have any big effect on the galaxy because their kinetic luminosity become very puny. But they are objects that are radiating at 1 to 5% of L. Eddington. We believe that the actual effect is happening from the monster quasar that radiating close to L. Eddington.
There's an interesting theoretical issue here.
Mm-hmm.
That you have so much kinetic luminosity you're creating that, all you need to do is really, to get an outflow, is to get something that escapes speed, so a tenth or less of your speed, right, from that radius. And yet it's not happening. And yet, at these higher speeds, the temperature of the gas that's absorbing is a much smaller fraction of the kinetic temperature. You think it would be harder to create 10-4 degree gas moving at 5,000 to 8,000 kilometers a second than it would be to create 10-4 degree gas moving at 500 to 800 kilometers a second.
Nobody does see the 500 to 800 kilometers a second gas.
Well, I understand. But even if we just focus on this one component, there's still an issue about a physical issue. About why is it that it's so inefficient in training gas at this larger radius?
Assuming that gas is still there again, some of it might have been cleared away.
I'm not sure what the question is. I mean, he sees slower gas
Yeah.
and more of it, or at least by numbers,
Yeah.
more of it. So I'm not quite sure what
But
you're
that's
asking.
on mass flow.
You're saying why doesn't, I mean, the point is the hot gas is going way faster. It's even going faster than, say, 1,000 kilometers a second.
The dynamical time, R over V, is way less than 10 years.
Yes.
Okay. So if you were to do the thought experiment of setting out this very fast outflow, okay, with enough kinetic energy to entrain a lot more mass than this, why isn't it happening? Because you're right that on a 10 to 8 year time scale, you might well have a mass bottleneck, right? But on the time scale R over V,
Yes.
where you think the system would relax to some sort of local equilibrium, it's
In the million-year timescale, basically.
or less actually.
So you want to entrain more mass,
Well,
but you need then a supply of mass, right?
yeah, but again, over some long period of time, it can't happen. But why can't it happen on that short amount of time is the issue. I guess you have some sort of whittling out process. So if the outflow is very collimated, and then it's just some sort of boundary layer effect with some gas reservoir, it's only near the boundary of the outflow that you were training, right? Of course, by NA2,
To zeroth order, I think that's the picture.
then maybe you can explain.
Okay. So there's lots of room for looking at the theoretical side of it. Yes, I fully agree. There are several other very interesting enigma. How do you keep the two phases? And things like that. One quick question?
No, I think we can go upstairs and talk more because it's already 20 past.
Sure.
So you do have to catch a plane.
Yes.
So let's thank Nahum again.